4.3, expected value. It's a helpful kind of way of thinking about things if we think of probability as on a scale. So we call this the probability scale. So the maximum probability is 1 and the minimum is 0. So if something's definitely going to happen, it's going to have a probability of 1. Or if something is definitely not going to happen, then it has a probability of 0. Most probabilities of things kind of live in between. And all the probabilities of a certain event happening or not happening have to add up to 1. You can't have a probability that's more than 1 because you can't have something more than definitely happen. Sometimes I'm so excited about something that it might feel like it more than definitely happens. But truly, an event has a probability between or equal to 0 and 1. So let's just think of an example that we feel kind of comfortable with by now about, let's talk about rolling dice. So if the probability of rolling a 3 on a dice is, well, there's 1 in 1 face out of 6. Now if I were to take my handy dandy calculator and go 1 divided by 6, I would get 0.16666666666. Okay, that would round to 0.17. So if the probability of rolling a dice is 1 out of 6 or 0.17, then the probability of not rolling a 3, this is actually a very powerful thing to know, that probability scale, because what I can say is 1 minus 0.17, which is going to equal 0.83. This is very helpful in the topic that we are about to embark on. So all games of chance are based on expected value. Which means like it takes into consideration the likelihood of a gain or a win or a loss. Is the game worth playing? That's a question that we always need to ask ourselves. And is it a game worth offering as a fundraiser, say? Because if the expected value, if the expected winnings are going to be positive, then that means that you can't use it as a fundraiser. Whereas if the expected value is less than 0, so if you're expected to lose money, that could be a good fundraiser. So the expected value formula is the probability of a win or gain minus the probability of losing or a loss. Sometimes there are 2 different prizes. So a helpful thing that I want to just to remind you guys, that a win, we're always going to add it, and a loss, we're always going to subtract it. Because the first example is only one with 2 options, either you win or you lose, whereas the second example that we're going to go through, because there have been some questions on the provincial exam that have popped up with 3 different options instead of just 2. I just didn't want you to be thrown for a loop if you see that on a provincial exam. So a few things to note. Probability is easiest expressed as a decimal. It's really easy to go from 0.17 to 0.83 if you subtract the 0.17 from 1. It's just more easily manipulatable. However, if you feel more comfortable with fractions, come and chat with me, and I can show you that way. But if you feel comfortable with the decimals, more power to you. And the gain is always going to be the winnings minus the cost. right? Because if the game costs $2 to play and you win 10, you didn't really win 10, right? You actually won 8 because you have to take into consideration the cost to play. Okay, so let's look at our first one. So 2 options. A game has 5 cards, one of which is the winner. The game costs $1 to play. If you select the winning card, then you win $4. Find the expected value and how much would you win or lose if you played 200 times. So first things first, we want to find the expected value, and this will be for one game. And then how much will you win or lose if you played 200 times? This is going to be a B part. As I rate A. Very good, Woodyard. Very good. Okay. So for A, let's find the expected value. So like a good little math student, I'm going to say expected value is probability of a win times the winnings or the gain. And I'm going to subtract the probability of a loss times the loss. So I'm just going to set up my formula here. So the probability of a win is going to be, okay, it's out of 5 cards and only 1 is a winner. So 1 in 5 chances. So if I were to get that as a decimal, I would go 1 divided by 5 and I get 0.2. The gain is going to be how much you win, $4 minus the cost to play, which is going to be 1. So your gain, you're ahead $3. So the probability of a loss is going to be 1 minus 0.2, because that's the probability of that win. Just showing you where you got that from. So 1 minus 0.2 is going to be 0.8. And how much did you lose? What's your loss? Well, it's $1 because it costs $1 to play. So now what I'm going to do is I'm going to give each one of these a color here, and then we're going to substitute. So the loss, I'm going to highlight in magenta, and then our gain I'm going to highlight in blue. Our probability of losing I'm going to highlight in yellow. And then the probability of winning I'm going to highlight in green. So the probability of winning is going to be my green, so that's going to be 0.2 times the gain, so that's the amount, that's going to be $3. I'm up $3. Minus the probability of the loss, which is 0.8, minus how much you actually lose, which is $1. So I'm going to say, okay, 0.2 times 3 is going to be 0.6. So 0.6 minus, 0.8 times 1 is going to be 0.8. 0.6 minus 0.8 is going to be negative 0.2. And if I were to say this in dollars, you're going to lose 20 cents each game. So this is a good game from a fundraising perspective, but it's not. It's still kind of a fun game for people who are playing because games of chance are kind of fun, but it's not necessarily a sure thing that you're going to win. In fact, overall, if you play a lot, you will on average lose 20 cents per game. So the expected value is minus 20 cents. In real speak, this means you lose 20 cents per game played. So if I were to play 200 times and I lose 20 cents per game, how much would you win or lose if you play 200 times? Well, I would go 200 times negative 0.20, which is going to be negative $40. So you would lose $40 over 200 games. And that's just approximate. We know that we're going to talk more about experimental probability versus theoretical probability. Theoretically, you're going to lose $40, but depending on how that specific experiment went, maybe you're going to make money. Maybe you'll lose more than $40. Reality versus like actual experimentation or actually doing the event sometimes happens differently than what we expect. That's the cool thing about probability. It doesn't predict the future. It just predicts what the general trends will be over a long period of time. Okay, 3 different options. Let's talk about this one. So, Pick a Marble game is a game that involves picking one marble out of a bag. In the bag, 32% of the marbles are red, 4% are green, and 64% are blue. It costs $2 to play, and the prizes are listed below. So if you pick a red marble, which I'm going to highlight in magenta, there's a 32% chance of winning, and you will win a stuffed animal valued at $10. If you pick a green marble, there's a 4% chance of you doing that. You get a stuffed animal valued at $15. And if you pick a blue marble, then you don't, and there's a 64% chance that you'll do that, you win nothing. So, calculate the expected value for the game. So remember what I said, we're going to add the winnings and we're going to subtract the losses. So this event here, we're going to be adding. And this one, it's also a win. We're going to be adding. This one will be a loss because even though you win nothing, you have paid $2 to play. So if I were to write the formula for this one, I'm going to call this win 1, win 2, and this is the loss. Okay, so the expected value here is going to be the probability of win 1 times the gain for the gain 1 plus the probability of win 2 times the gain of 2 minus the loss 1, so probability of a loss multiplied by how much you lose. So we know the probability of winning, the first one. That's going to go right there. So if I were to kind of go off to the side a little bit, let's calculate our values here. So the probability of a win for 1 is going to be 0.32 because that's 32% as a decimal. Oh. And we're going to figure out what our gain for number 1 is. So gain 1 is going to be $10 because you would win a stuffed animal worth $10 minus the $2 that you play, so it's going to be $8. What about the probability of a win 2? Well, our win 2 is going to be 4%. So as a decimal, that would be 0.04. How much do you gain if you have the second option for winning? So gain 2. You still have to pay $2, but this stuffed animal has a value of $15. So the gain, the second gain is going to be 15 minus 2, which is going to be 13. The probability of a loss is going to be 64% or 0.64. And the amount for the loss is going to be the cost to play the game. So it's going to be $2. Okay, so let's plug in our values here. So the probability of the first win, or win 1, is going to be 32%. How much do we gain if we win in that way? It's going to be $8. So these are just the values that I calculated here. Since there are 2 ways of winning, that's why we're adding 2 things. Okay, so the probability of the win 2, oh sorry, I kind of did that weird. The probability of the win 2 is going to be 0.04. The second gain, you're going to gain $13 instead of 8, minus the probability of a loss is going to be 0.64, which means you will probably lose. And the amount for that loss is going to be $2. Okay, so 0.32 times 8 is going to be 256, so 2.56 plus 0.04 times 13 equals 0.52 minus 64 times 2, so 0.64 times 2 is going to be 128. So if I go 256 plus 52 minus 128, I'm going to have an expected value of 180. So this is for one game. This is how much you're expected to win. So since it's positive, it means that from the player's perspective, if you play it over enough time, you're going to be coming out with more money or more stuff in this case, because we're talking about stuffed animals, more stuff than when you left the game. Now, from a fundraising perspective, this is not ideal because you're not going to be making money, right? If the expected value is positive, it's good for the person playing it, but not good for the people fundraising. So remember, this is for one game. If we played, say, 10 games, the expected number of winnings or the expected amount of stuff that you would get would be 180 times 10, which would be $18.